example, page rank calculation. In page rank calculation, we will use an additional constraint. The result vector should be partitioned in the same way as the input vector. So the output becomes the input for the another iteration of matrix vector multiplication. This involves partitioning the matrix into square blocks rather than types. Relational algebra operations. So there are relationally many operations. It involves the retrieval of small amount of data. For example, a query may ask for a bank balance. Actually, such queries are not useful application of MapReduce. However, many operations are not described using a common database query primitives, even if the queries are not executed within the database. So consider this example. A relation is a table with column headers called attribute and a row of the relation are known as tuples. The set of attributes on the relation is called schema. And if we write a relation R of A1, A2, etc. An, the relation name is R and its attribute is A1, A2, etc. An. So consider this relation. This is the column heading and these are the tuples. A relation can be stored as a file in a distributed file system. So in that DBMS, we are using tables for storing a relation. In DBM, distributed file system, we use a file for storing the relation. The elements of the file are known as tuple. In the previous case, in the DBMS, the rows are known as tuples, and here the elements of the files are known as tuple. The standard operations include refers to that of the relational algebra, and the queries are written in SQL. So different relational algebra operations are selection, projection, union, intersection, and difference, natural join, grouping, and aggregation. The first operation is selection. We will apply a condition to each tuple and it produces as output only those tuples that satisfy C. So what do you mean by tuple in distributed file system? It is the element present in the file. So we will apply some condition to each and every elements present in the distributed file system and produces some tuples. So then next operation is projection. For some subset S of the attributes of the relation, produce from each tuple only the components for the attributes in S. So here we are applying the operation on some subset and it is usually denoted as pi S of R. It produces only some tuples. Some components are extracted. Next operation is union, intersection and difference. Set operations. So multi-set operations are also there. Then natural join. Given two relations, compare each pair of tuple, one from each relation. If the tuple agree on all the attributes that are common to two schemas, then produce a tuple that has components for each attribute in either schema or agrees with two tuples on each argument. Okay, next one is all equi-join. Joins where the tuple agreement condition involves equality of attribute from the two relations that do not necessarily have the same name can be executed in the same manner. The next one is grouping and aggregation. Given a relation R and partition its tuple according to their values in one set of attributes G is called grouping attribute. Then for each group, aggregate the values in certain other attribute. So aggregations include sum, count, average, min and max. And the meaning are obvious. So we note a grouping and aggregation operation in a relation R by Yx of R, where X is a list of elements that is either a group attribute or an expression theta of. The result of this operation is one of the tuple for each group. The tuple has a component for each of the grouping attribute with the value common to tuple component for each aggregation and with the aggregated value for selections do not need the full power of MapReduce. That can be conveniently done in map portion alone. So we are not applying this selection in the reduce portion usually. We will apply it map portion alone. Some cases we will apply it in reduce portion also. The implementation of MapReduce of selection is denoted using sigma c of R. So we are having two functions, map function and reduce function. In the case of map function, for each tuple in R, we will test a condition. Selection operation means there will be one condition and we will be applying condition for each of the tuples. So in map function, for each tuple, we are applying the condition and it will produce what is the output of a map reduce function. Map function output of a map function is a key value pair. So if we apply a condition to a tuple, the output of a map function will be a key value pair which satisfies certain condition. That is both key and value of the tuple is extracted. In the case of reduce function is an identity. Its symbol passes every key value pair to the output. So output value has in the either case key value pair. Even if it is a map or reduce, it is a key value pair. A relation can be obtained using value components of the output. Then computing projections by MapReduce. Projection is performed similar to selection because a projection may cause same tuple to appear several times and the reduce function usually eliminate duplicates. And the projection is usually denoted as pi s of r. If we are applying projection on the map function, then for each tuple, construct a tuple T by eliminating from T those components whose attributes are not in S. So we will eliminate all the tuple whose components whose attribute are not in S. The output will be again a key value pair. Then reduce function. For each key T dash, if produced by any of the map tasks, there will be one or more key pairs. The reduce function turns the tuples T dash, etc. T dash into T dash. So it produces exactly one pair of T dash for the key. Observe that the reduce function is duplicate elimination. This operation is associative as well as commutative, so a combiner associated with each map task can eliminate whatever duplicates. Union, intersection and difference by MapReduce. So first consider the union of relation. Suppose we are having two relations R and S and map task will be assigned chunks from either R or S. That operation is known as union, either R or S. Map task doesn't really do anything except pass their input tuple as key value pair to the reduced task. The latter need only eliminate duplication as for projection. And map function turn each input tuple t into key value pair. And in reduce function associated with each t, there will be either one or two values. Produce output tt in either case. In order to compute the intersection, use the same map function. However, the reduce function produce tuple if both relations have tuple. If the key has a list of values tt, list of values tt and associated with it, then the reduce task for t should produce tt. However, if the value list associated with t is just t, then one of R and S is missing. Means value list contain just a t means one of either R or S is missing. So we don't need tuple for that intersection. So in map function, turn each tuple into key value pair. And in reduce function, if key t has a value list tt, then produce tt, otherwise produce nothing. To compute the difference, only way a tuple can appear in the output is if it is in R but not in S. The map function can pass from R and S through but must inform the reduce function whether the tuple come from R or S. We shall use the relation as a value associated with key. So in map function, for a tuple t in R, produce key value pair tr, and for a tuple t in S, produce a key value pair. For a reduce function, for each key, if associated value is R, then produce tt, otherwise produce nothing. Computing natural join by map reduce. Consider joining R, A, B, C and S, B, C. So here natural join means find tuples that agree on their B components. That is, second component from the tuple of R and first component of tuple of S. So we use B values of tuple from either relation as key. The value will be other component and the name of the relation. So reduce function can know where each tuple came from. So map function for each tuple A, B of R produce the key value pair B, R, A. For each tuple the same algorithm works if the relations have more than two attributes. You can think A as all those attributes in the schema of R but not in S. So B represents both schemas and C represents attributes only in the schema of S. The key represents all the values in all attributes that are in schemas of both R and S. The value for a tuple of R is the name of R together with all values of all attributes belong to R but not to S. And the values for tuple S is the name together with the values of the attributes belong to S but not R. Reduce function looks at all the key value pairs with a given key and combines all those values from S with those values of S in all possible way. For each pairing, the tuple produced has the values from R, the key values and values from the S. Grouping and aggregation by MapReduce. As with join, grouping and aggregation means where there is a one grouping attribute and the other one is the aggregation. For example, R of ABC be the relation and we will be applying YA theta of B of R. Map will perform the grouping and reduce does the aggregation. A map function for each tuple ABC produce key value pair AB and reduce function each key represents a group. Apply the aggregation operator theta to the list of B1, B2, etc. Bn of B values associated with key A. The output pair is AX where X is the result of theta to the list. For example, if theta is sum, then X equal to B1 plus B2 plus etc. up to Bn. And if theta equal to max, then it is the largest of B1, B2, etc. Bn. So if there are several grouping attributes, then key is the list of all the values of the tuples of all the attributes. If there is more than one aggregation, then reduce applies each of them to the list of values and produces a list consisting of key and the components of all grouping attributes. So next is matrix multiplication. If M is a matrix with element Mij in row I and column j, and N is another matrix with element Njk in row j and column k, the product is Mn and is the product matrix P with element Pik. So, as usual, the matrix multiplication, if the first matrix is of the order m by n, the second matrix must be of the order n by r. This n and this n must be the same, as you all know. So here, the product matrix equal to product matrix equal to Mij into Njk. Mij into Njk. Okay, how will you represent a matrix as a relation with three attributes? Three attributes are there: row number, column number, and the value name. So it will be represented like this. So Mij, first one is the row, and the second one is the column, and last B equal to value. So row, column, value. Row, column, value. With the tuples I, j, m, I, j, this is the value of the particular element with row I and column is j. So matrix can be viewed as a relation n, j, k, w with tuples j, k, n, j, k. If you are using sparse matrix means the number of elements, there will be large number of zeros. So we can omit the tuples with elements as 0. So it is possible that I, j, k are implicit in a file. So you can rather than written explicitly with the element itself. So map function will be designed to construct the ijk component of the tuple. So we have a matrix and the relation is like this ijk. So we need to, in MapReduce, IJK is computed. So the product Mn, this Mn is using an operation natural join followed by grouping and aggregation. Natural join of M, I, J, V and N, J, K, W have only attribute J in common and would produce tuples I, J, K, V, W from each tuple I, J, V in M and tuple J, K, W in N. So the five components of the matrix element represent. So what is the element of tuple of M? M means tuple of M means M consists of I, J and V and N consists of J, K and W and J is common. J is common here. Okay. In both matrix J is common. So it will, the five component tuple represent this one Mij, Njk. So in the product you will be having only the elements are multiplied. Here the element is V. Here the element is W. So VW is V into W is performed. Elements are product are find out. So the component of the product matrix will be I, J, K and B, W. V cross W is the product. That means we are performing multiplication of M and N. Okay, once we have this relation as the result of one map reduce function, we can perform grouping of aggregation with I and J as grouping attribute and the sum of V into W as aggregation. So we can implement this matrix multiplication as a cascade of two map reduce operation. So here we are using grouping and aggregation and this can be implemented using matrix multiplication. A matrix multiplication is also a series of two map reduce operation. The map function for each matrix element Mij, the key value pair. What are the elements of M, I, J, V? Okay, this is the relation of M. So what is the key value pair? So J, comma, M, comma, I, Mij. This is the key value pair of first matrix. So key value pair of second matrix is J, comma, N, comma, K, comma, Njk. These are the elements. Then that is last component is the last component, this one and this one are elements of matrix. Okay, also this first one, this I is the common one. Okay. Rather they are the names of the matrices, a bit of indicating whether the elements come from M or N. Okay, next one is a reduce function. For each key J, examine its list of associated values. For example, for M, Mij, this one is the element, last component is element, and also this one is also element in N. This is element. So first one is the matrix name, and next one is this one is the matrix name, and next one is the component which is not in common. This is component which is not in common. So it produces a key value. It produces a key value pair with key equal to Ik. Ik means those components are not in common. So it will produce a matrix product of I, J and N, J, K, where these N, J elements are common. Grouping and aggregation by another map-reduce function. Map function. This function is just an identity. That is, for every input element with key ik and value v, this produces a key value pair. Also, in reduce case, for each key ijk, produce the sum of list of values associated with this key. In reduce function, actually we will get a key and a list of values. That's why here we are producing a sum of list of values associated with the key. So result is a pair ijk where v is the value of the element in the ith row and jth column of the product matrix P. Matrix multiplication with one map reduce step. So use a single map reduce parts to perform matrix multiplication P. So we need to do more work into two functions. So start up by using map function to create the set of matrix elements that are needed to compute each element. So an element in M or N contributes to many elements of the result. So one input element will be turned into many key value pair. The keys will be ijk, where I is the row of M and k is the column of N. So in map function, for each element mij of M, produce a key value pair ik, M, j, mij, where k is equal to 1, 2, etc. up to the column number of N. Similarly, njk. So reduce function. In reduce function, for each ik will have an associated list of values mj, mij and nj, njk for all possible values of j. So it needs to connect the two values on the list for the same value of j. After that, sort by j. Then jth values on each list must have their third component as mij and njk extracted and multiplied. And the result is paired with ijk in the output of the reduce function. If the row of matrix M or column of matrix N is too large so that it is not fit into the main memory, then reduce task will use an external sorting. In the third step, we had done a sorting method. So if the elements are not fit, then we will go to external sorting. If it is a sparse matrix, then we will expect fewer values to be associated with one key. Extensions to map reduce. Map has a number of extensions and modifications, and they are built on a distributed file system. They manage very large number of tasks that are instantiations of the small number of user written function. Also, they incorporate a method for dealing with most of the failures that occur during the execution of the job. If it is failure, then you have to restart that job from the beginning. Workflow systems. So, two experimental system, Clustra, which is from University of Wisconsin, extend MapReduce from a simple two-step workflow to any collection of functions. So here we are using a cyclic flow graph where whose arc A derives B represent the fact that function A's output is input to function B. So 5 functions f through j pass data from left to right. So flow of data is acyclic and no task is needs to provide data out. And function h takes its input. So we have function f g h I j. So this h takes its input from the pre-existing file and output of x is at least one output of I or j. So in analogy to the map and reduce function, the workflow can executed by many tasks. So in map reduce function, there will be a number of maps and reduce. Similarly, this workflow can be reduced into many tasks and assign a portion of input to the function. So here also one master controller is there for dividing the work among the tasks, similar to the map reduce. And like map task, each task implements a function f which has an output file of data destinated for each of the tasks that implement the successor function of f. These functions are delivered by the master at appropriate time after the task is completed. In MapReduce parser also, after task is completed, it will send the result to the map controller. Similar to that, here also, each task implement a function and output is sent to the master, indicating that its work has completed. Understanding the HDFS architecture. So HDFS is presented as the master and slave architecture. HDFS master is called the name node and slave is not data node. Name node serve that manages the file system, namespace, and adjusts the access to client. It divides the input data into block, announces that data block will be stored in data node. And data node is a slave machine that stores the replicas of the partition data set and serves as the data as the request comes. So it performs block creation and deletion. HDFS divides the file into one or more blocks, and these blocks are saved in a set of data nodes. Usually, replication factor of 3 is placed. First copy is placed in local node, second copy is in local rack with the different node, and third copy is stored in different rack with different nodes. And default size of HDFS is 64 MB. Understanding HDFS components. HDFS is managed with a master-slave architecture with the components name node and data node. The name node is the master of HDFS system. It maintains directories, files, and manages the blocks that are present on the data nodes. And data nodes are the slaves on each machine and provide the actual storage. They are responsible for read and write data requests for the clients. Secondary name node. This is responsible for performing periodic checkups. If a name node fails at any time, it can be replaced with a snapshot of the image stored by the secondary name node. So secondary name node is saved for periodic checkpoints only. MapReduce is implemented using master-slave architecture. Classic MapReduce contains job submission, job initialization, task assignment, task execution, progress and status update, job completion related activities, and these are managed by job tracker node and executed by task tracker. Okay, client application submits its job to job tracker. So this is client and it will send an input to job tracker. So this is job tracker. The client will send input. Actually, the input is divided into clusters. These are clusters. This one is the input. The input is divided into cluster and it is fed to job tracker. Job tracker, aim of this one is to calculate the number of map and reduce. So then it is fed to task tracker. Aim of task tracker is to start the execution of job. Now, task tracker copies the resources to a local machine and launches JVM to map and reduce program over the data. Along with this, task tracker periodically sends update to the job tracker. It will periodically send some like this, periodically send some data to the job tracker, which can be considered as heartbeat that helps to update the job ID, job status and usage of resources. So in client server model, client sends the input. Actually, the input is divided as across the clusters and this input is fed to job tracker. Aim of the job tracker is to calculate the number of map and reduce operations. It commands the task tracker to execute the job. Job of the task tracker includes copying the resources to the local machine and launches JVM to map and reduce program. And task tracker will periodically send updates to the job tracker. So this is very important one. Map reduce is managed by master-slave architecture with components job tracker and task tracker. Job tracker is a master node of the map reduce system which manages jobs and resources. It tries to schedule each jobs also. And task tracker are the slave. Job tracker is the master and the task tracker is the slave. It is responsible for running all the map and reduce. Understanding the HDFS and map reduce architecture by plot. In this plot, both HDFS and map reduce master and slave components have to be included. Name and data node are from HDFS and the job tracker and task tracker are from MapReduce paradigm. So both paradigm consist of master and slave candidates have their own specific responsibilities to handle map and reduce and HDFS. Each master-slave candidates have their own responsibility to handle map function, reduce function as well as HDFS function. The first layer is a map reduce layer and the following is a HDFS. Okay, this one is the architecture. So it consists of HDFS and MapReduce architecture. First layer is a MapReduce layer, and then it is followed by HDFS layer. So it is a master-slave approach is used. Again, it is a multi-node cluster. Each input is represented in different clusters. So what are the components of MapReduce? Task tracker and job tracker. So job tracker, actually the client sends data to the job tracker and input is stored as clusters. So there will be clusters, and these clusters from these clusters data are sent to job tracker. Job tracker sends this data to task tracker. So this is the case of master and slave. There will be no job tracker. There will be task tracker alone. And this job tracker, the job tracker in master will assign some task to task tracker of slave. Okay. Similarly, in the case of HDFS layer, the components are data node and name node. So there won't be any name node in the slave. So Hadoop is the top level Apache project and is very complicated Java framework. To avoid the technical complication, Hadoop community has developed a Java frame that has added an extra value to Hadoop features. So they are considered as Hadoop sub-projects. So MAHOUT is a popular data mining library. It includes machine learning algorithms, clusters, classification, regression, statistical model, etc. So it is a scalable machine learning library. And it is distributed under friendly Apache software license. So it is to build a vibrant, responsive and diverse community to facilitate discussions about the project and its potential use. The following are the companies that are using Mahout: Amazon, AOL, Drupal and iOffer. Lucid Work Big Data, Hadoop, Twitter, Yahoo. These are using Hadoop. Then next one is Apache HBase. Apache HBase is a distributed big data store for Hadoop. This allows random real-time read-write access. So this is designed as a column-oriented data storage model inspired by Google Bigtable. So HBase is used by Yahoo, Twitter, Mahalo, NING, W upon BEOH. So next one is Hive. Hive is a Hadoop-based data warehouse like framework developed by Facebook. It allows users to fire queries in SQL-like languages such as HiveQL, and it is highly abstracted to Hadoop MapReduce. This allows SQL programmers with no MapReduce experience. So user might not have any experience about MapReduce, but he can work on this framework. The next one is Pig. Pig is a Hadoop-based open source platform for analyzing large-scale dataset via SQL-like language, and that language is known as Pig-Lative. It provides simple operations and programming interface for massive and complex data parallelism computation. It is easier to develop and more optimized and extensible. Yahoo and Twitter are primary Pig users. For developers, the direct use of Java API can be tedious or error prone. So Hadoop provides two solutions that enable making Hadoop program for data management and data analysis with MapReduce easier. That is Pig and Hive. Apache Scoop. So Apache Scoop provides Hadoop data processing platform and relational database. So it is mutual data tool for importing data from relational database to Hadoop HDFS. It works together with relational database such as MySQL, Oracle, Microsoft SQL Server, etc. Apache Zookeeper. It is also a Hadoop subproject used for managing Hadoop, Hive, Pig, HBase, SOLR, etc. Zookeeper is an open source distributed application designed with fast Pagos algorithm based synchronization and configuration and naming services such as maintenance of distributed application. Zookeeper. In programming, Zookeeper design is very simple data model and it divides into two parts, server and client. A cluster of Zookeeper serves as a leader which accepts and coordinates all writes, and the rest of the server are read-only, and it will serves as read-only copies of master. If leader goes down, any other server will start serving all the requests. That means any other server become the master. Zookeeper clients are connected to the server on the Zookeeper service. The client sends a request and receives a request, accesses the observer events, and sends a heartbeat via the TCP connection with the server. For a high-performance coordination service for distributed application, Zookeeper is a centralized service for maintaining configuration, information, naming, and providing distributed synchronization and group services. Each time they are implemented, there is a lot of work that goes into fixing the bug and race condition. Apache SOLR. It is an open source enterprise search platform from the Apache license project. This allows building web application with powerful text search, page search, real-time indexing, dynamic clustering, database integration, and rich documentation. It is written in Java and it can run as standalone server to serve the search result. And it is integrated with, it can easily integrate it with any programming language. Due to all these features, this search server can be used by Netflix, AOL, CNET, and Zappos. Empari is very specific to PhotonWorks. It is a web-based tool that supports Apache Hadoop cluster, supply, management, and monitoring. It handles most of the Hadoop components like Hive, Pig, HBase, Super, Scoop, Hcatalog as centralized management. It is able to install security based on Kerberos authentication protocol over the Hadoop cluster. It is a role-based user authentication and auditing function for users to manage integrated LDAP and Active Directory. Understanding the basics of MapReduce. It doesn't have a cluster or uses message mapping interface. However, a more realistic use case is when the data doesn't fit in one disk but fits on a distributed file system. or already lives on Hadoop-related software. MapReduce is a programming model that works in a distributed fashion, but it is not really the one that does. So it might illuminating to describe other programming models such as MPI and bulk synchronous parallel. Okay, how to process the big data? We can use the tools like R and several machine learning techniques. It requires high configuration machine. So distributed processing is a key to handle such kind of data. We can use MapReduce programming model for implementing distributed computation. So to process data, we need parallel processing, which means processing over large computation. It can be either obtained by clustering the computer or increasing the configuration of the machine. Using the computer cluster is an ideal way to process big data. Okay, Google MapReduce research. It is a white paper written by Jeffrey Dean and Sanjay. So it is a MapReduce is a simplified data processing software on large clusters. So its implementation runs on large clusters with commodity hardware. The data processing is easier for programmers to perform various operations. The system takes care of input data, distributes data across computer network, processes it in parallel, and finally combines output into a single file. So it helps in terms of cost and time saving system. So it efficiently use the computer resources. So our aim is we have map and reduce function. So input data is divided as chunks and it is distributed over the network. Usually it is processed in parallel. Map and reduce functions are there, and after the execution done by the reducer, it is combined into a single file and it is aggregated and it is output to next layer. So map reduce, programmers need two phases, map and reduce. To design map function, we need to generate a key value pair. To generate a set of intermediate key value pair, and reduce function will merge all the intermediate keys. Both map and reduce function maintain map reduce workflow. So the function of reducer is to execute the code, and once it is completed, it will combine all the output, and it is or once the map output is available to it, it will start execute and it will output it to the next processing. So MapReduce assumes that maps are independent and are executed in parallel. So maps are independent and executed in parallel. So algorithm, if map and reduce is independent of all other ongoing map and reduces in the network, the operation will run parallel on different key and list of data. A distributed file system spreads multiple copies of data across different machines. So this offers reliability as well as fault tolerance. If one master node fails, the responsibility of master node will be taken care of by MapReduce daemon. What is the responsibilities of MapReduce master node? Execution of job, scheduling of mappers, reducers, combiners, partitioners, monitoring of success, as well as failure of individual jobs and completion of the batch job. So Apache Hadoop process the distributed data in the parallel manner by running Hadoop MapReduce jobs on servers near the data stored on Hadoop's distributed file system. Companies using MapReduce include Amazon, eBay, Google, LinkedIn, Trovit, Twitter. Introducing Hadoop MapReduce. MapReduce model can be implemented in various languages. Java framework is a popular one. It processes vast amount of data in parallel on large clusters of commodity hardware in a reliable and fault-tolerant manner. So MapReduce paradigm is divided into two phases, map and reduce. And it is mainly deal with key value pair of data. So map and reduce task run sequentially in a cluster and output of map is fed to reduce phase. All the input element in MapReduce cannot be updated. If the key value pair is changed, it will not be reflected in the input files. So mapper output will be pinged to the appropriate reducer grouped with the key attribute as input. The sequential data will be carried out in a parallel manner. So MapReduce programs transform the input data present in the list form into output data that will also be in the list format. The logical list translation process is repeated twice in the MapReduce phase. So this is repeated by fixing the number of mappers and reducers. Listing Hadoop MapReduce entities. So 4 components: client, job tracker, task tracker, and HDFS. Client will initialize the job. Job tracker monitors the job. Task tracker executes the job. HDFS stores the input and output data. Understanding the Hadoop MapReduce scenario. There are 4 main stages of Hadoop MapReduce data processing. First step is loading of data into HDFS, execution of map phase, shuffling and sorting, and finally execution of reduce phase. So loading of data into the HDFS. The input data needs to be loaded to the Hadoop directory, so it will be used by MapReduce. So Hadoop distributed file system will divide the data set into small chunks and it stores them to data node in cluster by taking care of replication factor for fault tolerance. So a number of copies of that data will be stored. So it will eliminate the problem of failure. So it will be reliable. All the data splits will be performed by task tracker for map and reduce task in parallel. So actually the input data is fed to the Hadoop directory and here Hadoop file system divide. This is HDFS, Hadoop file system, and input is divided into some chunks and it is replicated. So this replication will avoid fault tolerance. All the data splits will be processed by task tracker. So these data splits are processed by task tracker. So some alternatives of HDFS with Hadoop components. First one is Scoop. Next Flume. Executing the map phase. That is the second phase. So executing the client application starts the Hadoop MapReduce process. The map phase then copies the job resources and stores it to the HDFS and requests job tracker to execute the job. Actually, the clients will submit its job to the job tracker. Client will send a job to the job tracker. Okay. Then map phase in the job tracker. Map phase. There is a phase in job tracker. This map phase copy the input and store multiple copies in SDFS. And after that, this job tracker send a request to job task tracker to execute the job. So function of job tracker is to initialize the job and retrieves the input and split the information and creates a map task for each job. It will call task tracker to execute that particular job. Map task read this data and split as key value pair and provide it to the mapper method, which then produces intermediate key value pair. So usually map function will create an intermediate file. So this will contain at least one output for each key value pair. So this is the input list, and for each input we will be storing some key value pair. The function of mapper is to extract key value pair, and from the output we will get a list of key value pair. The list of key value pair is generated such that key attribute will be repeated many times. Key attribute will be repeated and it is reused in the reducer for aggregation. As far as format is concerned, mapper output format values and reducer input values must be same. So after the completion of this map operation, now the job is with task tracker. After the execution, task tracker will keep all the result in buffer storage. The next one is shuffling and sorting. To optimize the map reduce program, this is used. Okay, as soon as mapper function, mapper output from map phase is available, this intermediate phase will be called automatically. After the completion of map phase, all the emitted intermediate pairs will be partitioned by the partitioner. So first is mapper function. Mapper function will generate the key value pair and it will be stored in intermediate files. So once a map is completed, a intermediate key value pair will be partitioned by the partitioner. So output of the partitioner is sent to the mapper will be sorted out based on the key at the mapper side. Output from the sorting is stored into a buffer memory available at the mapper node of task tracker. The combiner is you open the reducer itself. So in the reducer itself, combination is done. Combination of the combining the output is done at the reducer itself. So here there may be some compression is allowed. The data returned from combiner is then shuffled and so after obtaining the data it is shuffled and sent to reduced node. To speed up the data transmission, you need to compress that data. So compression of data will speed up the data transmission. The mapper output will be stored to buffer data, buffer memory, and if the output size is larger than the threshold, it is stored into a local disk. So what are the steps? Map reduce, So reducing phase execution. As soon as mapper output is available, task tracker in the reduce node will retrieve all the available partitioned maps output data, and they will be grouped together and merged together into a file and assigned to a process with a reducer method. Finally, sorted out data is provided to reducer method. So there will be input and it will be divided into a number of chunks, and the chunk is fed to map process, and map process will produce key value pair, and these key value pairs are passed to partition. What is the function of partition? Partition partitions the key value pair, and then these key value pairs are sorted and shuffled, and then it is written into an intermediate file, and reducer will produce the output, and all the output of reducing process are combined using combiner, and there will be some compression also done at this stage, and finally the outputs are combined and we will get the final output. Reducer receives a list of input values from the input key list value and aggregates them based on custom logic and produces the output key. Okay, from the map function, it will produce key value pair, and these key value pairs are fed to the reducer method, but the format will be key list value, that is key followed by a list like this, key followed by values. Values will be a list v1, v2, etc., and aggregate them based on some condition, and finally we will get a key value pair. The output of the reducer method of the reducer function will be written to HDFS format. So finally output will be written to a HDFS, that is Hadoop distributed file system. So we will get a input list, key value list, and it is aggregated, combined. Here we will use some compression in some cases. After that we will merge all the result and final output is obtained. Understanding the limitations of MapReduce. MapReduce is difficult to leverage for convolutional logic that is not as simple. For example, real-time streaming, graph processing and message passing is too difficult. Data querying is inefficient over distributed unindexed data. If the index of the data is generated, it needs to be maintained when the data is removed or added. So we can't parallelize the reduce task to map task to reduce the overall processing time, because the reduce tasks do not start until the output of the map task is available. So reducer's output is purely dependent on the output of, reducer's input is purely dependent on the input of map. Also, we can't control the execution of map and reduce task. So we can configure a slow start for reduce task at the instance when the data collection starts as soon as map task complete. Long running reduce task can't be complete because of poor resource utilization, either if reduce task is taking too much time to complete or fails if there are no reduce slots available. and this can be solved using yarn.